So in this video lecture, we are going to discuss about grade 11 topic, that is waves, and in that the subtopic is beats. So you should have watched the earlier video in which there was a small demonstration given by me about the beats. Link is given in the description. That is the part 1. Please do see that. And now let's start the mathematical derivation. So we should have two waves, and let me call the first wave as S1, that is equal to A sine omega 1t minus k1 x, and the another wave is S2, that is A sine omega 2t minus k2 x. Now the difference in frequencies of both, because this term represents angular frequency, that is 2 pi f1, and here this omega 2 will be 2 pi f2. This is 2 pi by lambda, the wave number, and here also again 2 pi by lambda 2, this is lambda 1. So since these two are the expression for the sound waves, and definitely the sound waves are longitudinal in nature, so I am not writing y is equal to a sine omega t minus kx, because then the particles are oscillating about y, their displacement is about y, and the particles, they are situated, I mean the wave is moving along x-axis. So this equation represents, had it been y, something like this, y is equal to a sine omega t minus kx. That means you have a transverse wave which is moving along positive x direction like this, and the particles are oscillating along y, right? So the displacement varies along y-axis. So I am not writing y because sound waves are longitudinal, but definitely whenever the sound waves, they move along positive x direction, the particles, they displace along the same direction. So the wave is going in this direction, the particles are oscillating along this direction. So ideally the expression should have been something like that: x is equal to a sine omega t minus kx, the equation of the sound wave. But there seems to be a small confusion. Here also x, here also x. This is the displacement of the particle along x-axis, whereas this is the position of the particle from the origin. So both are x-axis, I mean both are same symbol, so this will create a confusion. So all the good textbooks have eradicated that confusion by taking displacement s. Of course the displacement is along x-axis, right? So these two sound waves, they have different frequencies, different wavelengths, but they are traveling in air with the same speed v, that is approximately 340 meters per second, right? Now these two sound waves, definitely they are compressions and rarefactions, but I just tend to draw them for the sake of the easiness to understand the concept. Now these two waves are definitely the sound waves, definitely they are longitudinal. I am just showing them as a transverse waves. Now they choose to meet at one point, they will meet at one point over here. So this wave has frequency f1, wavelength lambda 1, frequency f2, wavelength lambda 2. They are going to meet at one point, and this is the point in the medium, and I'm going to select this point as origin. So there is this particle of the medium which is located at the origin. So these two waves are meeting here. So our task becomes very simple. I'm simply going to substitute here 0, x here as 0. So our displacement s1 will become a sine omega 1t, and the displacement s2 becomes a sine omega 2t. Now let me clarify that there is a very small difference in the frequencies. So if f1, I mean to say f1 minus f2 maximum, we can take 10 hertz, that I will explain you at the end. So if you are taking the frequency as 500 hertz f1, then this has to be maximum 510 hertz or 490 hertz, right? So the difference in the frequency has to be maximum maintained 10 hertz, that I will reveal later on why. Okay, now since these two waves are superposing at this point, so we need to apply the principle of superposition. So the net displacement of this particle under the effect of these two waves will be equal to s1 plus s2. So I'm just going to add them: a sine, then omega 1t plus a sine omega 2t. For the sake of the easiness of derivation, we have kept the amplitude to be the same, right? All right. Now, a comes out to be common, so S net is equal to A. Then here we have sine omega 1t plus sine omega 2t. All right. Now I'm going to use this expression in maths, sine C plus sine D, that is equal to 2 sine, let me write with another pen, 2 sine C plus D by 2, and then multiplied by cos C minus D by 2. Please remember this mathematical identity. So I'm going to take this part as C and this part as, D. Okay, so we have a similar identity, sine C plus sine D. So this is sine C plus sine D, and now our answer is going to be something like this. Net displacement of this particle due to the superposition of this wave, that is equal to 2 sine omega 1 plus omega 2 by 2 t plus, multiplied by cos of this omega 1 minus omega 2 by 2 times t, right? So this is C minus d by 2 and this is C plus d by 2 term over here. Now I'm going to pull out this 2 common. So this is 2a. Now let me write this as, this is of course S net, that is equal to sine, this is 2 pi f1 plus 2 pi f2 by 2. Please do not cancel this 2, we need it, right? And cos of again 2 pi f1 minus 2 pi f2 divide by 2. Again, do not make any cancellations here, you will understand why, right? So I forgot t over here. Now let's write this again. S net is equal to 2a. I'm just rearranging. Now I will explain you what am I going to do here. This part, that is this 2 pi, needs to be taken common here. So cos, this becomes 2 pi. This is f1 minus f2 by 2. Then we have this sine function, that is sine 2 pi in bracket f1 plus f2 by 2. Now if we closely look at this entire expression resembles an SHM equation. See how come. This can be also written as, right, the SHM equation is displacement, it can be x or y, that is equal to a sine omega t, or S net is equal to a cos omega t plus phi, right? I'm choosing the phi to be 0. Now see, I'm going to very carefully select this part as the amplitude, and see this entire part, that is sine omega 1 plus omega 2 by t. So that is this part. Now you might have this question, sir, why are we not equating with this one? I'll give you the answer shortly. So what do we have here is the following. So this entire expression, the coefficient of this entire sine term, the coefficient of sine term is a. So this entire coefficient of this sine term, this becomes amplitude. So I'm just going to write down amplitude a dash, this is a dash, right, is equal to 2a, that is equal to 2a then cos 2 pi f1 minus f2 by 2, right? So this entire equation becomes S net, that is equal to a dash, right? Then you have sine 2 pi f1 plus f2 by 2, correct? So if you look at these two equations, this sine omega t, that is sine omega 1 plus omega 2 by 2 times, I forgot t here and t here, right? I forgot t here, like this, right? So this part is the amplitude and this is the sine term. All right, now let's discuss that why I did not compare this entire expression with this one. See guys, now what happens is when these two waves with different frequencies, when they meet here, it is experimentally observed that this particle will oscillate, will undergo SHM. It will start performing simple harmonic motion with frequency F1 plus F2 by 2, the average frequency, that is the F average of these two. So that is experimentally seen that this particle oscillates with the frequency which is average of these two. So that is why I am selecting the sine term to be over here, not the cos term, because cos term has F1 minus F2 by 2. So that means this particle oscillates with F1 plus F2 by 2. So that means this part has to be taken over here, right? So the cos term goes actually inside the amplitude part. I hope this is very well understood. Once again, I'll let you know what I have spoken just now. When you have two waves of different frequencies, this particle oscillates with the average frequency. So that means either your answer could be this or this. Now, if you look carefully here inside, it is F1 minus F2 by 2. So I can't take this cos term to be the main term, right? So over here, I will have to select this entire term to be this term, and then the remaining portion as your amplitude. So this one, right? Now, on the basis of this, what else we can observe? We see that in normal SHM, the amplitude doesn't change with time. You can very well see this amplitude is going to remain constant, doesn't depend upon the position, doesn't depend upon the time. But look here. Here amplitude is purely a function of time. So as time changes, this amplitude will increase and amplitude will decrease, amplitude will become zero. So this amplitude keeps on fluctuating with sound, with the time, sorry. So since we are dealing with the sound here, right? So amplitude is directly proportional to the loudness. So at this point, if amplitude changes with respect to the time, so the loudness is also going to change with the time, right? So we will hear a louder sound, then we will hear again a zero sound, I mean practically a sound with zero loudness, like that. Okay, so now let me turn back and let's talk about this in detail, about the maximum loudness and the minimum loudness time. Then I will come to beats again. So we had an expression of A dash that is equal to 2A cos 2 pi F1 minus F2 by 2 times T. This was the amplitude, right? Now I want this amplitude to be maximum. So for amplitude A dash to be maximum, right, this entire part should be 1. So that means cos of 2 pi F1 minus F2 by 2 times T should be equal to either plus 1 or minus 1. See, in physics, minus 1 doesn't mean minimum. It means maximum in the opposite direction, right? So if you are unaware about the cos graph, let me just tell you that the cos function is something like this. Just remember this one, right? And this is plus 1, this is minus 1, this is 0, this is pi by 2, this is pi, this is again 3 pi by 2, and this is 2 pi. So at different angles, you have different values of the cos function, right? So let's move ahead. So I want this cos function to be maximum, plus 1 or minus 1. So I'll take 0, I'll take pi, I'll take 2 pi, like that, right? So this whole angle that is 2 pi F1 minus F2 by 2 times T should be equal to either 0, or it should be equal to pi, or it should be equal to 2 pi, right? And for the function to be minimum, let me simultaneously also talk about the minimum part as well. For A dash to be minimum, that means the sound is 0, right? The amplitude is 0. For this entire amplitude to be minimum, I want the cos function, that is 2 pi F1 minus F2 by 2 times T should be 0. For that, I should be taking pi by 2, then 3 pi by 2, 5 pi by 2, and so on. So this whole angle, that is 2 pi F1 minus F2 by 2 times T should be equal to either pi by 2, then 3 pi by 2, then 5 pi by 2, and so on and so forth, right? So I will take different time intervals here. All right, so I'll take the first time. Let me take the first time 2 pi. Okay, I now can cancel out these two, so I'm left with pi f1 minus f2 times t. Let me take this as 0, and I'm going to mark this as time t1. You will understand why I have done this, right? So now time t1 is 0. I'm going to get the loud sound at time is equal to 0. Now I will do the simultaneous calculation over here. Again, this 2 gets cancelled. Now for here, pi f1 minus f2, I'll take the first value. Okay, this is time t2. You will understand why I have taken in sequence t1, t2 and so on. I'm going to take this as pi by 2, the first value. Pi gets cancelled. So I'm going to get the value of t2 as 1 by twice of f1 minus f2. So this is the time when I will get the first 0 sound, right? This is the maximum sound, then again 0 sound, and so on, like this. Now the second loud sound is at pi f1 minus f2, and that is at, this is taken now pi gets cancelled. Okay, I always keep on forgetting this one. I'm going to write down t1, then t2, and then t3. So again, t3 value is 1 upon f1 minus f2, right? So this is the second time when I'm going to get the loud sound, right? I'm going to write over here again pi times of f1 minus f2. Now I'm going to write down this as t4. That is equal to this I have already taken. Now 3 pi by 2. Okay, this gets cancelled. So the value of t4 I'm going to get as 3 by twice of f1 minus f2. Correct. Now the last one that I'm going to do here is the following. That is pi times of f1 minus f2. That is equal to 2 pi, right? So this is taken. Now this is what I'm going to write. Cancels, times t5 again, right? So the t5 value is twice of f1 minus f2. So these are the times when I'm going to get the loud sound. These are the times when I'm going to get the 0 sound. Now you will understand why I have written like this t1, t2, t3. So you can see that this is the least value of time. Then the next time is this one, because see, this number is bigger and this is smaller. So I'll get a loud sound, then I'll get 0 sound, then I will get loud sound, then I'll get 0 sound, then I'll get loud sound. So the time gap between two loud sounds, either I can take these two or I can take these two. The time gap between two loud sound itself is known as 1 beat. Correct. So that means I can also say that the time gap between the two beats, I mean two loud sound, is the time period of beats. Time period of beats means it is the time difference between two loud sounds. I can take the difference of this and this, or this and this. I'll get the same answer. That is 2 by f1 minus f2 minus this one. So I'll get this one. And then the reciprocal of this is the frequency of the beats. That is the reciprocal, that is f1 minus f2, which is also known as the beat frequency. Either you can calculate the beat frequency from here, or you can repeat the similar thing from here also. You can take the difference between two low sounds and you will again get the beat frequency, beat time period. Reciprocating, you will get the beat frequency. Okay, so this looks good in sequence. Loud sound, then immediately you will get at this time 0 sound, then again at larger time compared to this, that is this one, right? This is 0, then half of this, then double of this, then again 3 by 2, then twice. So loud sound, 0 sound, loud sound, 0 sound, then again loud sound. So here in this diagram we are given these two waves, and the displacement of this wave is S1, this is S2. Now these two waves are superposing. Now the frequencies of these two waves are F1 and F2. The difference in frequency is very small, right? And I have to explain that why. Now when these two waves, they superpose, you will get the net wave like this, which is varying in amplitude, so the amplitude is 0, then the amplitude becomes larger. If you look carefully, the amplitude becomes larger, and somewhere over here the amplitude is largest, right? And again the amplitude keeps on decreasing, becomes 0, then amplitude keeps on increasing. So what we have done is we have connected the net waves top point and the bottom point with an envelope, so you get something like this, right? So the amplitude varies with time. You can see that the amplitude varies with time, and this is the net frequency that I was talking about, f1 plus f2 by 2. So this net point where these two waves interfere or superpose, they oscillate with the net frequency f1 plus f2 by 2, and the amplitude varies with the time. Now I should explain you why the beat frequency f1 minus f2 should be equal to or less than 10 hertz. That is due to the fact that if this is a human ear, and if one sound wave enters your ear, it will hit your tympanic membrane, that is the eardrum. Then from there, the waves are being produced, electrical signals are being produced. Then from auditory nerves to brain, that signal is actually processed. So it takes a certain amount of time, that is 0.1 second. So before that, if any other sound wave enters your ear, then your ear is simply going to reject that. So the time gap between two sound waves to be heard clearly is 0.1 seconds. So the reciprocal of that is 10 hertz. So that means if two waves come before 0.1 seconds, then the frequency is going to be more than 10 hertz, and your ears are simply going to reject that. So this was my attempt to explain you beats. Please do comment if you have any doubts, and thank you very much for watching the video.